Seriously.
Okay.
Missed the drawing.
Oh, that explains it.
Missed it.
Okay. Now, look up here at my ellipse. Do you see this red dotted line and this blue dotted line? That looks like what from what we just did? Our dental floss. And as we move around, okay, these are going to always add up to be the same thing. Right here, 11.41. Okay, those two lines are continuously adding up to be the same thing. Okay, I can make this ellipse look more circular or more oval shaped, more squished, and we're still going to have these two lines add up to be the same thing. That is the geometric property of an ellipse, okay? And I wanted to be able to show you that using something that you can actually do yourself, okay? Which is why we did the dental floss activity, okay? Now, we're going to transition to notes. You are welcome to take notes on your green ellipse and label things on there. Or if you want to take notes in your notebook, you can, or a combination of both. I will let you do either one. But we're going to go ahead and talk about and name everything on our ellipse. Okay, so we just talked about using our dental floss, that an ellipse is the set of points, the sum of whose distances from the 2 points is a constant. So the distance from point to foci will always add up to be the same thing in an ellipse. And the brads, so now the holes in your paper, are your 2 foci. 1 focus, 2 foci. How would you describe the shape? Oval.
It's elliptical.
Circles and elliptical.
I thought that was
Like when the petals down.
I'm with you. Okay, so a circle is a special type of an ellipse. Okay. But an ellipse kind of looks like a circle that's been squished a little bit. Do you agree? Okay. So one side of our ellipse is going to be longer than the other. That's what makes it have that squished shape. You agree? All very technical terms here. Whichever side, like if you put your ellipse and you make 90-degree angles, okay? One side of your ellipse is going to be longer than the other. The side that is longer is what we call the major axis, and that's what's going to pass through. It's going to pass through our center. Our foci will be on there, but then we're going to call the end points of that major axis our vertex points. And then the minor axis is basically going through the short side. Thank you. Okay, so we are going to plot 6 total points. Wait, 1, 2, 3, 4, 7 total points to make this ellipse. Okay, we're going to have to find the center because everything is based off the center. We will find our vertices. we will find the end points of the minor axis, and so then we'll be able to draw our shape, and then we'll have to plot the foci points as well. Okay. So let's talk about, we could have on our graph, we could have a horizontal ellipse or we could have a vertical ellipse. Basically, is the major axis horizontal or is the major axis vertical? Okay. So just like we did with a parabola, we have two different standard form equations. Okay. If you're labeling anything on your green sheet, make sure you're labeling that those holes are the foci, and then make the end points and label them as vertex 1 and vertex 2. Okay. I don't know if you're labeling on your green sheet or not, but you could be doing that. Okay. All right. The standard form of an ellipse. First of all, before you write anything down, what do you notice that is different about this equation compared to parabolas?
That one's divided. And that one-
Okay, well don't panic, but I'm going to point this out right here. Okay, both x and y are squared. In parabolas, we only had one variable that was squared. Here in ellipse, we have two variables that are squared. Well, a and b are going to be numbers. So you could have like 25 or 36 down there for your denominator. Okay? We do want the standard form equation to equal 1. So that we can identify a and b. All right? Notice how a is bigger than b. And so since a is associated with x minus h squared, that's how we know this is going to be horizontal. Because a, which is bigger, is associated with x. So HK is now what we're going to call the center. The parabola is kind of the odd man out. We use HK for the vertex. A parabola doesn't really have a center. Okay, but an ellipse and what we talk about tomorrow, a hyperbola, they're both going to have two vertex points. So we need what's called the center, and that's going to be our HK. All right, so you're going to plot the center first. Your vertex points are going to be A units away from the center. So since this is horizontal, we are going to move out horizontally A in both directions to create our two vertex points. Okay. We are then going to use B to plot the endpoints of our minor axis, and then we can get a shape. Okay, so whether you're drawing this on your green ellipse or in your notes, I don't care, but this is what's happening. And then the foci, I'm going to go ahead and have you label. I'll tell you how to find C here in a moment. But the foci are going to be C units away. And that's a calculation we're going to have to make separately. Just give me a moment to get there. Okay. All right. What do you think is going to be different about a vertical ellipse?
Maybe the Y's with the A.
Exactly. The y is going to be with the a squared. The bigger denominator is going to tell you which direction this ellipse is going to be. I'm going to say open, but that doesn't make sense. Okay. So now a squared is under y. Okay. You'll always see the equation as x minus h squared and then plus a y minus k squared, but the bigger denominator is going to tell you which direction it opens. So this is going to open vertically. We still have a is bigger than b. We still have a center of hk. But now we just have an ellipse where the major axis is vertical. Our foci are vertical. And it looks more like, I don't know, I was going to make a comparison, but.
Yeah. One of those little stand-up ones.
Okay. Looks more like a mirror than a compact.
Yeah.
No, I'm saying I was like,
Oh, or a rugby ball. What? No, I just know that the ball is.
Okay. Do you want me to label the A, B, and C on this ellipse as well?
I think we're good.
Yeah.
Okay. Vertices are still AOA. Minor endpoints are BOA. Foci are COA. The only difference is the direction in which we count them. What's nice though about an ellipse is that the a squared, like vertically, you're going to move vertically, you're going to move whichever number is associated with its denominator. Horizontally, you're always going to move the number that's associated with its denominator. Okay, so even if you can't remember if it should be horizontal versus vertical, whatever denominator x has, square it and move that distance horizontally. Whatever denominator y has, square root it and move that distance vertically. And then you might be able to tell if it's skinny up and down or left and right. Okay, now I want you to look at the major axis. Well, that didn't work. How long is the major axis? If we go from vertex to vertex, what would that distance be? A plus A, right? So it's the length 2A. Okay? How about the minor axis? From minor endpoint to minor endpoint, how long is that? 2B. Okay? What would it look like if A and B were the same?
A circle.
Then we would have a circle. Okay? And that's why I say a circle is a special kind of ellipse. Okay? Now, we've been talking about that the foci are COA from our center. Let's actually talk about how to find C. C squared equals A squared minus B squared. Okay. If we had a circle, C would equal 0. Okay, and our foci would come all the way to the center. Okay. Now, we have one more thing to calculate, and then we'll get to an example. But we have something called eccentricity. And eccentricity is when we take C divided by A. And this is going to measure how oval the circle is. Or the oval the ellipse is. which end of the scale would be more circular? Is a number closer to 0 or a number closer to 1 more circular versus more oval?
Closer to 0.
Okay, eccentricity is up here. This is pretty oval, isn't it?
Yeah.
This is pretty,
So,
well, we're trying to get circular. So the closer we are to 1, the more ovally we are. Okay? All right. Are you ready? Let's graph. Oh man, Mrs. Holman, this isn't in standard form.
What the heck?
How do we know it's an ellipse, Dallas?
Because there's an x squared and a y squared.
There's an x squared and a y squared. More specifically, which you'll see why tomorrow, they have the same sign for their coefficient. Like x squared and y squared are both positive, which means when we rearrange and complete the square, then we will have an x minus h squared plus a y minus k squared. Okay, but since this is in that general form, we do need to complete the square how many times?
twice.
Because we need an x minus h squared and we need a y minus k squared.
It's okay. It's okay.
It is okay. So let's go ahead and we need to group x squared and 6x together so that we can complete the square. And we need to group 4y squared and negative 8y together. But didn't I tell you you can only complete the square if your leading coefficient is 1? So we're going to need to factor out a 4 from y squared minus 8y so that we can complete the square. And then I'll move 9 over and account for the 2 mystery numbers we're going to have to add to the left side. We also need those on the right side. So what completes the square here for our x's? 9. What completes the square here for our y's? 1.
Oh.
However,
But that's
it's being multiplied to 4, so 1 times 4 gets put on the other side. More times than not, you will have a coefficient you're going to need to worry about. So when you complete the square, please remember to multiply it by that coefficient when you balance out your equation. Okay? So what we have is x plus 3, the quantity squared, plus 4 times y minus 1, the quantity squared, equals 4. We're getting closer to that standard form equation, but we do need our equation to equal what?
1.
Right now it equals 4.
Do you divide by 4?
We divide by 4. So our standard form equation is x plus 3, the quantity squared, over 4, plus y minus 1, the quantity squared, over 1, equals 1. It's really not that bad. And in my opinion, ellipses are the easiest of the 3 to graph. There's really not a lot of work to it. Okay? So, Brayden, horizontal or vertical? Brayden thinks horizontal. Sydney, why would he think that? Good question. Help her out, Brayden.
It was a 50-50 shot.
All right, Dallas, you have an idea.
4 is bigger than 1.
4 is bigger than 1. Okay? 4 is bigger than 1. And the bigger number is under the x squared. Okay? Now, 4 and 1 are our denominators. But remember, they're a squared and b squared. So this denominator is a equals 2 because this is like 2 squared. And this denominator is b squared, so we're going to say b equals 1. If the 4 was under the y minus 1 squared, then it would be vertical. And a would be under the y. Okay? So, our center. H comma K. Kinley, where's our center? Negative 3, 1. Always make them opposite. Negative 3, 1 is our center. Okay? Our vertices. And sometimes you'll hear me call these major vertices. But, I mean, really, they're just vertices. But I like to emphasize the fact that they're on our major axis. Okay? Our major vertices, we are going to move horizontally 2 from the center. So our major vertices are going to be at negative 1, 1 and negative 5, 1. Like we did Monday, plot them, then write them down. Okay. Our minor axis endpoints are B away, and since B is associated with Y, we are going to move 1 in the vertical direction. So our minor endpoints are negative 3, 0 and negative 3, 2. Look at that, guys. We have an ellipse. What?
How did you find it on your
I just moved B away in the direction it was associated with, so I looked at the denominator.
Oh, that's easy. Wow, you were right.
Okay, Emily, do you see what I mean by, like, Sydney didn't know if it was horizontal or not, right?
Yeah.
Not a problem, Sydney, because if we go 2 in the horizontal direction and 1 in the vertical direction, and then graph it, we can see that it's a horizontal ellipse. Okay? So you don't really have to. Now, we need our foci and eccentricity. So please remember that c squared is a squared minus b squared. Well, a squared was 4 and b squared is 1. So c is radical 3. Okay, well, radical 3 is really not a nice number to graph, right? But we know that radical 3 is bigger than 1, but it's not quite 2 because the square root of 4 would be 2. Okay, so the square root of 3 is a little bit smaller than 2. So from our center, we're going to go almost 2 away for our foci. And since we moved horizontally, we changed the x-coordinate. So I'm going to write our foci as negative 3 plus or minus radical 3, comma 1. Now, if your c value was a nice integer value, please do not write 1 plus or minus 2. You know what those numbers are. Okay, but if it's irrational, I will let you write the foci together. Okay, and then last but not least, our eccentricity. I just want you to identify it. C over A. And then that's all I want you to do. Okay.
Oh my gosh. It's the never hanging way.
So do we have to like plot the red points on the graph?
Just follow it around.
I do want you to plot the foci, yes.
Oh.
Okay? I just made them a different color because they are inside of our graph. They're not actually on our graph. Okay? All right. We're not going to go through this entire problem, but please write this down with me. I'm going to go ahead and put this in standard form for you. X plus 2, the quantity squared over 4, plus y minus 1, the quantity squared over 9, equals 1. Is this vertical or horizontal? Vertical. Do you notice how in this one, our denominator with the y is larger? So now, A is 3 and B is 2, but A is associated with y this time because it's vertical. Riley, do I need to let you leave early?
No,
You're good? Okay. So we would have a center of negative 2, 1. And then we would move 1, 2, 3 vertically because our y denominator is 9. We would move 2 horizontally because our x denominator is 4. You know what I mean? Like, that's not bad at all, is it? Okay, I graphed it and then I went and identified all the points. If c squared is a squared minus b squared, 9 minus 4 is 5. So c would be radical 5. And our foci, this time we would write as negative 2, and then the 1 would be the plus or minus 5, because we would have to move vertically. And I know that radical 5 is a little bit more than 2, because radical 4 is 2, so I can plot them approximately right there. Yes. Like this number right here. Okay, so from here we moved vertically. So I took the center and I added and subtracted radical 5 to my y coordinate since we moved vertically. My homework assignment will be posted by first lunch. Okay? What? Do you have to say help?
No, I leave after 3 hours, so I get but it's okay. Check it
It is possible that during third hour I could get it up, but I'm not going to promise it.
It's okay, I'll check it.
Okay. I'm not here tomorrow. Please be on your best behavior.
Of course.
Yes.